In this problem, we're going to find VC of t for t greater than 0, and we're going to be utilizing the problem-solving strategy entitled second-order transient circuits. And if we look at our circuit, when the switch opens, it doesn't remove either the capacitor or inductor in the circuit, so that's why we're going to have a second-order circuit in this case. So the switch opens at t equals 0. So if we look at our problem-solving strategy, the first step is to write the differential equation for the circuit. So let's draw our circuit for t greater than 0. Here's a single loop circuit. I'm going to define a current I of t in that circuit. And now let's apply Kirchhoff's voltage law around this loop clockwise. So we'll have V sub c of t plus 1 times I of t plus 0.25 di dt equal to 24. Now we've got one equation and two unknowns, but if we remember about the capacitor, we know that I of t is equal to 0.8 dVc dt. So now let's substitute this in for I of t. So we have V sub c of t, we have 0.8 dVc dt plus 0.25 times the derivative of 0.8 dVc dt equal 24. And performing some of the operations here, we get 0.2 times the second derivative of the capacitor voltage with respect to time plus 0.8 dVc dt plus V sub c of t equal 24. Now let's divide through by the 0.2 or multiply through by 5. So now we get the second derivative of the capacitor voltage with respect to time plus 4 dVc dt plus 5 V sub c of t is equal to 120. So here's our differential equation for our circuit. Now, our next step is, okay, what's the characteristic equation? And our characteristic equation is s squared plus 4s plus 5 equal to 0. If we use the quadratic equation, we'll have minus 4 plus or minus the square root of 4 squared minus 4 times 1 times 5 over 2. The roots here are minus 2 plus or minus j1. So one of our roots is minus 2 plus j1. The other one is minus 2 minus j1. So we have complex roots. So we have an underdamped response. And the form of our solution then is going to be K1 e to the minus 2t cosine t plus K2 e to the minus 2t sine t plus the K3. You say, well, wait a minute, where did that K3 come from? Well, if we look at our circuit, when this switch is open, we're still going to have a source left in here, and that would give us our forced response. So our K3 in our equation here, this is our forced response. Here, these two terms make up our natural response. So now our task is we've got to find K1, K2, and K3. So now let's go in step 5. Let's go to start looking for those. So at t equals 0 minus, here's our circuit. The circuit we assume is in steady state. the capacitor is an open, the inductor is a short. If we look, then there's zero current here, so IL of 0 minus is 12 over 6, or 2 amps. And then this would tell us that there's 2 volts across this resistor, so VC 0 minus would be 24 minus 2, which is 22 volts. And you know, for instance, we know continuity of voltage for the capacitor is 22. Continuity of current for the inductor says that IL of 0 plus is going to be 2. Okay, so let's look at this circuit. And what I'm going to put on here is I'm going to say, well, okay, here is IL of 0. We're going to look here at VC of 0. Okay. And we know that IL of 0 minus equals IL of 0 plus equals IL of 0, and that's equal to 2 amps. And then we note, you know, that this is also I of 0. So we know that I of t is C dV C dt. And we can solve that and say, well, dV C dt is 1 over C times I of t. So then the value of the capacitor voltage derivative at t equals 0 is 1 over C times I of 0. So that's 1 over 0.8 times 2 is 2.5. Okay. So there is the value of the derivative of the capacitor voltage at t equals 0. Okay, so we drew this circuit. We said, well, we know this is 2. We're really interested in what is the rate of change of the capacitor voltage at t equals 0. And this is how we were able to solve for it. So now, we know that our solution then is still the form we had, but let's go in and look at t equal infinity real quick. And if we look, this is a pretty easy circuit. The capacitor is open, the inductor is short, so there's 0. So V sub C of infinity then is 24 volts. So now, our solution is V sub C of t, K1 e to the minus 2t cosine t plus K2 e to the minus 2t sine t plus K3. So for instance, we plug in t equal infinity. That's going to give us K3. So now, we know that VC 0 minus equals VC 0 plus equals 22. And this is going to be K1 plus K3. So we got 22 is equal to K1 plus 24. So that gives us that K1 is equal to minus 2. Now, we've still got one other term. We need to take the derivative of VC of t. So dVC dt then is K1 times minus 2 e to the minus 2t cosine t minus e to the minus 2t sine t. Again, we're having to use the chain rule here. Or really not chain rule, really it's the derivative of, we've got that function e to the minus 2t cosine t we've taken the derivative of, and then we got k2 times minus 2 e to the minus 2t sine t plus e to the minus 2t cosine t, and then plus, of course, the derivative of k3, which is 0. So here we got to go in and do the derivative of a product. Okay, e to the minus 2t cosine t. Alright, now we've got all that. Let's now go in and evaluate this derivative at 0. Okay, so if we plug in t equals 0, that term goes away, and we're going to have minus 2k1. So here, this is 0, this is 1, this is 1. Down here, this is going to go away, and we're going to be left with k2 is equal to 2.5. So now we have minus 2 times minus 2 plus k2 is equal to 2.5. So k2 then is minus 1.5. And this gives us our solution, which is v sub c of t minus 2 e to the minus 2t cosine t minus 1.5 e to the minus 2t sine t plus 24 volts.